Hi, my name is Sadra and I'm applying for TA position at Neuromatch Academy. I have a background in computational neuroscience and a strong interest in neuro AI. My research involves using machine learning and statistical modeling to analyze brain data, and I enjoy teaching complex concepts in an intuitive way. Today, I walk you through polynomial regression and how we structure design matrix for it. So, so far, we've worked with linear regression, which is great for capturing simple regression between inputs and outputs. However, real-world data is often more complex. That's where polynomial regression comes in. Polynomial regression is an extension of linear regression where we introduce higher degree terms of our input variables. This allows us to model curve relationships. For example, if we have a data follows a quadratic terms like y equals x squared 2 minus x minus 2 plus a noise, a simple linear regression model wouldn't capture this curvature well. But if we introduce a squared, cubic, or higher order terms of x, we can fit a polynomial regression model that better represents the underlying trend. Mathematically, a polynomial regression model of degree k looks like y equals theta 0 plus theta 1 multiplied by x plus theta 2 multiplied by x powered by 2 plus and go on until you reach to theta k multiplied by x powered by k plus an epsilon, where theta values are the model parameters we need to learn from our data. However, to fit this model using linear regression techniques, we need to structure our input variables properly. This leads us to an essential concept that our design matrix. For simple linear regression, the design matrix looks like x equals x as there are matrix and x equals to 1 columns of 1 and columns of x, where the columns of 1s correspond the intercept terms of x of theta 0. For polynomial regression of order k, we extend this to x is that's it. X as our matrix have the columns of 1, x, and x powered by 2, x powered by 3, and go on until you reach to x powered by k. Each additional column represents a higher degree transformation of x. If we have a multiple inputs features, we apply the same expansion to each one. Let's now implement this in Python. Okay, here we have a function that you're gonna just complete a part. That's it. And that's here. And you're gonna complete this function that gonna get two inputs, that's x and order, that are their arguments. X is in the array input vector of of shapes that have n samples, and order, that is a scalar, a polynomial regression order. And this function gonna get these two x and order and returns an in the array that's design a matrix for polynomial regression of shapes, samples, and order plus one. Okay, your students gonna create and design matrix here. Okay, here you have conditions that say if x dot ndim equals 1, x gonna be x bracket colon and comma none. Okay, if x is a 1D array, it gets reshaped into a column vector n and 1. This ensure that matrix operations correctly when stacking polynomial terms. And another things that we have here is create a column of ones, shape in samples and ones to represent the intercepts termed x powered by 0 and that's gonna be 1. The term is crucial for polynomial regression because the model typically includes a bias term that we discuss about it. Iterates through each polynomial degree from 1 to the order, and it's the things that this function gonna do, this for loop's gonna do. And then after that, it's going to compute x powered by degree, which generates the respective polynomial features. Use MPH stack. That's a method that we have in NumPy library to horizontally stack these columns to design a matrix. You're going to concatenate this each matrix horizontally to each other to work properly and gives us this X matrix. Okay, And then you're gonna call this function that have for example, you have an order 5, x design have make design matrix x and order that we talk about it. It's gonna be input of our function, and then you're gonna print x design, uh, for example, from x to the first row and second row, and the first column and second column, and it's gonna give us this. Okay, there's two questions that you can ask, and it's why we should use this. If you don't use this, and you print the x shape of this our vector, it's gonna give you, for example, 3 and comma, and it's gonna be your. And then if you print the x, it's gonna give you 1, 2, 3, for example. And but if you use this condition, it's gonna convert it to this. That's our 3 and comma and 1. That 3 is our for the numbers of our rows, and 1 is number of our column. And it's gonna give us this like a matrix, and it's, as you see, is horizontally, and this is vertically. And H stack is gonna be concatenate this horizontal vectors to each other to create a great and better matrix that for us, that's matrix X. And that's it. Thank you.